Hello, students. We are dealing with 11.4. Had a few homework questions. First one was on number 7, which is like an always, sometimes, never, but in this case, it just says true, false. So let's see here. A cube has congruent edges, right? So again, that's a great one. That would be an always. But let's jump down here. Any pair of opposite faces of a right rectangular prism can be faces. Remember, in a prism, you have to have a shape on top and a shape on bottom, and they have to match. Now, notice it says a right rectangular prism. So the top and the bottom are directly over each other. And any pair of opposite faces could be a right rectangular prism. All right, so I want you to think about this. You have a right rectangular prism in the shape of like an Amazon box. Okay, and you know they come in many sizes, so they're not like cubes all the time. So let me ask you this. If you set that box down, is that a right rectangular prism? And you would most likely say, yes, that is. Now take that box and tip it 90 degrees up. So now maybe the thinner side is the base. Is that still a right rectangular prism? And you'd have to look and say, actually, yeah, the same shape is on top and bottom, and the sides are all quadrilaterals, in this case, rectangles. Okay, and if you roll it again, can you use any pair of opposite faces to create this? So just, again, picture it. Does it look the same? Now notice that is not quite the same as what you might find here in like question 1A, where the base of this one is shaded and kind of looks like, oh, it's this one right here. No, that is not the base. The base has to be the same for opposite faces. So the base is actually this one, a triangle, because out back is a triangle and those match up. All right. So yeah, man, it is an always. All right, let's take a look at the 13C was the next one, 13C. So this is where you're going to take like a thin piece of line. If you need to, kind of take a pencil and you can attach like a piece of paper or a card to it and then spin the pencil in your hand so that it kind of goes around really fast, and look at what three-dimensional shape is made. And we want to name the three-dimensional figure. Yeah. Yeah, so this one's maybe not quite so quick, but let's just say, what if, it feels like you should be able to do D. Like if you spin that one, right? Then this spins around here, and this spins around there. And then this one, as it spins around, is going to look like it connects back down here. I mean, that shape right there, three-dimensional shape, looks like a cone. So what I want you to do is think, this shape in part C doesn't really look like that. But if I drew a line straight across here, doesn't the bottom shape really look like that? And doesn't the top shape also really look like that? Of course, it's upside down. And so the idea here is not a truncated shape like we have in part A, but this one would be more of like, take two cones and kind of glue them together. And that would be it. That's it. No need to have a fancy name. You're just describing what it is. All right. Definitely not a polygon. Yes, that is very true. That is not a polygon. All right. And anytime you're rotating something or you're spinning something, you're going to be creating shapes that are circular in nature. And once they're circular in nature, it is no longer a polyhedra. It's no longer a three-dimensional like polygon. Okay. Let's see here. Number 21. Let's jump over 21, 21, 21. 32 faces made up of 20 regular hexagons, 12 regular pentagons. How many vertices are there? Now you could start this one from scratch and just, kind of go to town and be like, I'm going to try this and this and this. But the whole point of this type of problem is to use the relationship that has been discovered previously, which is Euler's formula. And Euler's formula asks you to know that vertices plus faces minus edges is equal to 2. And what do we say? We have 32 faces, okay, right? 32 faces made up of 20 regular hexagons and 12 regular pentagons. That's how it's broken down. So now as you look, you're trying to figure out how many vertices there are. So if you knew how many edges there were, then you'd be solid. So let's take a look. That would probably be, in my mind, that'd be maybe where I would start. I'd be like, hey, wait a minute here. What do I got going on here? I'm trying to find how many vertices, okay? I know how many faces, so I can plug that in. And edges, I'm not 100% sure on, so let's take a look. I want you to take a look as we go around. I'm going to start from the top and kind of work my way. So 1, 2, 3, 4, 5, 6. That's 6. I just went around that hexagon. Okay. Now, you have a lot of different ways to do this, but yes, I do have pentagons, but my pentagon sides will always match up with a hexagon side, so I don't really need to count the edges from the pentagon pieces at all. So those are already taken care of. So now I'm going to choose a different color here. I want you to notice something here. As I draw in the next one, 2, 3, 4, 5, 6. Notice they share a side. So if I think 6 sides and 6 sides, I now have shared a side, an edge. And I've double counted it. There's only one, but I've counted it twice. Okay. That really isn't a big problem as long as you know that it's happening. So if you keep going to the next one, you go 1, 2, 3, 4, 5, 6. These share a side. 1, 2, 3, 4, 5, 6. Those share a side. So I get a bunch of side sharing, right? And so however many hexagons I have, 1, 2, 3, 4, 5 at the top. Okay, each one of those has 6 sides. And if I keep going, what's great is every time that I put these together, I'm going to have an overlapping side. But not every side is overlapping. Every single side that went with a pentagon is not really overlapping with another hexagon. And if you use all of your hexagons to be able to create these, you can actually count them up. You will be double counting. So every hexagon that you have, when you think about how many line segments it has, yes, but 3 of those line segments per hexagon are double counted. Okay, so you need to take away those pieces. That's 3 additional per hexagon. Okay. What else could I do? I think if you wanted to, you could try to do something with the pentagons. So you could say, well, there's 5 that I just used, right? And do every pentagon, there's 5, 5, 5, 5, 5. Well, now when you think about it, there's also like these have to be considered as edges. So I have to make sure that I remove those as I'm counting. Okay. So yeah, so I can go through and do all the pentagons. That one's pretty quick because I know there's 12 regular pentagons, right? And 12 times 5 sides gives me 60 edges. So I'm already at 60 edges. That's not a big deal. The question then is, how do I get all of these little ones in between? Okay. All right. And yes, if you wanted to go pick up a soccer ball, you could kind of see how these things are staggered as you go forward. Anyway, that's the idea. So 2 different approaches that'll help you get the number of edges. Once you have edges and faces, go ahead and subtract them. Just subtract them and see what you get. And remember, vertices plus that number has to equal 2. And yeah, there's going to be a lot more edges than faces, so this number will be negative, and then you can solve that value. All right, let's take a look. And MC number 6. All right, let's take a look at number 6. What is the minimum number of faces that intersect to form the vertices of a polyhedra? Oh, this is a good question. How many Minimum number of faces that intersect to form the vertices of a polyhedra. Well, if you think about two faces coming together, those two faces would intersect in a line. But we're trying to form a vertex, so vertex won't do it with two faces, which means I need at least one other face. So you could get through here with three faces. And if those three faces intersect, then yeah, what's the minimum number of faces that intersect to form the vertices of a polyhedra? But I need all of them to intersect. Oh. Yeah, I think I'd probably go with that piece. So each time you get a vertex, it would be at the intersection of three lanes or three faces. So yeah, I think so. It's the minimum number of faces that intersect to form the vertices of polyhedron. Yeah. Unless it's saying how many total faces are there in the smallest polyhedron. I don't think that's what it means. Because we could do a tetrahedron that just has four faces. And those faces intersect to form the vertices of a polyhedra. I think they're going the other direction. Well, let's go find out. Let's go find out what the author thought. I was reading that question when I put it down as a requirement question. I was thinking of this as being when you think about like a three-dimensional shape like this, what's the minimum number of faces that intersect? You have to have three faces to form a vertex. You can't have two faces intersect. It won't form a vertex. It would form a line where those two intersect. And that's why a lot of those regular shapes don't work. The regular shapes are not gonna satisfy that. All right, let me hit pause here and grab the book. Well, looks like the authors and I are on the same page when it comes to this. So yeah, they also said the minimum number of faces that intersect to form the vertices of a polyhedron has to be three. And yeah, I'm trying to think if I could get more than that. For the polyhedron that we tend to have, I think three is what you always get when you're intersecting them. Because that's where the intersection of three line segments would be. But I guess you could have more if you have, let's go back to those. What page was it on? 720? Yeah, so here you've got like the icosahedrons. And that's a truncated icosahedron. That's icosahedron. Never mind. Go back to the regular shapes. Yeah, so if you take a look over here at some of these, I don't know if I can zoom in any more than that. Like, for example, in the shape that you see on top, what you've got is the front, the left, and the bottom. Front, left, and bottom, those intersect to form this vertex. Okay. And so you can kind of see the three line segments that are created here is the one between the front and the left, the one between the front and the bottom, and the one between the left and the bottom. Those three come together to form a point. You can have more than that, like we do here. There's actually four of these faces, and they're all meeting at a single point. This is the octahedron, or an eight-faced polyhedra. And then you can come down here to icosahedron. If you take a look here, this one gets a little bit crazy, but there's actually 5 faces coming together at each one. And down here, there's only 3. Down here, there's only 3. And there's actually, I mean, there's a reason for this. And so let me see. Maybe I'll bring that up in class on Monday because it's actually easier to show with hands-on materials. So if you're interested in this, bring it up on Monday, and I'll go in and I'll grab the polydrons, which are the kind of like Legos, but for polyhedron. So, all right, there you go. Have a good one. Off you go.